Well, welcome back. Excuse me. In this lesson, we are going to talk about the real number system. And we have talked about this before. The real number system consists of several smaller number systems. And the very first one that we ever talked about was called the natural numbers. And remember, we talked about the natural numbers were the counting numbers that you first learn when you're a baby. You have your first birthday, your second birthday, and those are all your natural numbers, 1, 2, 3, all those numbers. And then we learn about the concept of zero. So once we add zero to the natural numbers, we call those the whole numbers. So they're the same as the naturals, but they also include zero. Now, those two number systems together are called the integers, but with the integers, we also add the concept of negative numbers. So it's all of the positive and negative natural numbers and whole numbers. So those are called integers. And then we move up another level to the rational numbers. And the rational numbers are all the numbers that you can write as a fraction. Okay, if you can express it as a fraction, then it's a rational number. So that includes all of the terminating, which means any decimal number, or even repeating decimals like 0.33333. And as long as it's not an integer, a repeating decimal that's not an integer. So those are all the rational numbers. Examples of those are 1/3, so that would be a repeating decimal, a terminating decimal like 2/5 or 0.5. Here's another repeating decimal. Anything that can be written as a fraction would be a rational number. So that would lead to the question, well, what if it can't be written as a fraction? What kind of a number would it be if you can't write it as a fraction? Well, those are all the irrational numbers. So if it can't be written as a fraction of two integers or two whole numbers, then it's called irrational. So things like the square root of 7, there's no way to write that as a fraction, where it's a fraction of two integers or two whole numbers. Pi is another example of an irrational number. Okay, it's a non-repeating decimal. It goes on forever and never repeats. So any decimal numbers that don't ever repeat and they just go on forever would also be considered an irrational number. So when you put the rationals and the irrationals together, the number system we get is called the real numbers. So there you have it. That's what the real number system consists of. And there's other number systems as well that we'll talk about when you get into Algebra 2. Imaginary numbers are one of the things that we will deal with later on. So let's go ahead and talk about some irrational and rational numbers and how to solve problems with those. Here's a sports example. It says Major League Baseball has rules for the dimensions of the baseball diamond, which I'm sure you're aware of. It says the distance from the pitching mound right here in the center to home plate is 60.5 feet. Is that a rational number? Well, yes it is. That number could be written as a fraction. Okay, it turns out it's 121 over 5. So it is a rational number. Remember, rational numbers can all be written as fractions. The distance from first base to second base is 90 feet. Is that a rational number? Well, yes it is. We can write that as 90 over 1. Those are both integers, so that is a rational number as well. And the last question says the distance from home plate to second base. So home plate, when the catcher is trying to throw somebody out and they're stealing from first to second, the distance right across there from home to second is the square root of 16,200 feet. Can that square root be written as a rational number? Well, if so, it has to be written as a fraction. But if you were to plug that in on your calculator, it is a decimal number, but it doesn't terminate, it doesn't stop, and it doesn't repeat. So remember, the only decimals that are rational are the ones that either terminate or repeat. So it is not a rational number. So that value, the square root of 16,200, that distance from home plate to second base on your calculator, is this value that's given in the slide, but it doesn't stop, it keeps going. Okay, so we call that an irrational number. Here's the definition of irrational numbers, and the way that I would like you to remember this is an irrational number is a number that cannot be expressed as, and rather than the quotient of A over B, I think that's complicated and hard to remember. So how about if you just think about it as it cannot be expressed as, let's make this simple. How about if we just say a fraction, okay? So, and it's a fraction where a and b are integers. Okay, that's the important part, is they have to be integers. The set of rational numbers is the set of, the set of rational numbers and the set of irrational numbers make up our real number system. So that was, here's another way of looking at that in a Venn diagram. Here is your opportunity. Let's talk about how to classify numbers. So what sets of numbers do each of these numbers belong to? So what's going on with this decimal? Well, it looks like it's repeating. So remember, a repeating decimal is definitely a rational number. It can be represented as a fraction. So it is a rational number because we can write it as a fraction. And there's the fraction that's the equivalent. If you were to take 25 divided by 99 on your calculator, you would get 0.252525, and it would keep going forever. How about the square root of 36? Do you recognize that one? Turns out the square root of 36 is a whole number, right? That simplifies to the number 6. So that one is a whole number. It's also an integer, and it's a rational number. Okay, so the smallest set of numbers it belongs to, a whole number, but I would add to this, we've added 1 in here. This would also be a natural number, which is not in here, but that definitely is part of the natural number systems. So it's a natural number. That's the smallest set. It's a natural number, a whole number, and an integer. How about negative square root of 7? Okay, well remember the square root of 7 doesn't simplify. That one is irrational, okay, because the decimal value goes forever. It doesn't repeat and it doesn't terminate, so it is irrational. Here's a chance for you to check your progress. Go ahead and work on these, pause the video, come up with your answers, and I'll show you the solutions when you get back. All right, I hope you took a chance to try those. The square root of 10, is that a number that simplifies? Can we simplify that as a perfect square? And no, it is not. So that one turns out to be irrational. All right, negative 2 and 2/5. Can we write that as a fraction? Yes, we can. We can write that as negative 12/5. So that one is definitely a rational number. How about the square root of 100? Square root of 100 simplifies to the number 10. So that one is a whole number, an integer, a rational number, and again, this one we need to add. It is also a natural number. So please add that in there as well. And I'm going to abbreviate number here. Natural number. All right, we can also graph real numbers. Our problem on this slide says estimate the square root of 6 and negative square root of 3 to the nearest tenth. Okay, so we want to approximate those to the nearest tenth. So that's one decimal place. And then we want to graph them on a number line. So go ahead and punch in on your calculator the square root of 6 and see what you get. All right, and you should have gotten this decimal value. It keeps going forever, but to the nearest tenth, okay, we're going to look to the one place further. We're going to look to the hundredths place. Since that's a 4, we're going to cross all of those out, and we're just going to use 2.4. So I hope you remember your rules for approximating or rounding off decimals. Negative the square root of 3. Punch that in on your calculator. And you'll get negative 1.732050875. So to the nearest tenth. Again, if you look one digit over, it's a 3. Remember, if it's a 4 or less, then you cross those out and you only use what's there. If it's 5 or above, you round up. So those are our two values to the nearest tenth. Now we need to graph those on a number line. So here is what your number line would look like. So you can just put your integer values on your number line and then make a dot approximately where that would be. So 2.4, almost halfway there between 2 and 3. 1.7 is closer to negative 2 than it is to negative 1, right? It's about 3/4 of the way between negative 1 and negative 2. All right, here's a chance for you to try 3 more values. Go ahead and try these on your own. Pause the video and we'll look at the solutions when you get back. All right, I hope you took a chance to try a couple of those on your own. The square root of 5 to the nearest tenth will be 2.2. Negative the square root of 7 is 2.6. and that one's negative, right? Got to put that negative in there. Square root of 22 is about 4.7. So if we want to go ahead and graph those on a number line, it should look something like this. Okay, so square root of 5 is 2.2. It's closer to 2 than it is to 3. Negative 2.6 is closer to negative 3 than it is to negative 2. And square root of 22 is closer to 5 than it is to 4. Comparing real numbers. We want to replace the little gray dot with either a less than, a greater than, or an equal to sign so that we get a true statement. Well, what is the value for the square root of 7? Well, we said that was equal to 2.646, I guess I'll call it. And 2 2/3 is 2.6 repeating. So we need to figure out which one of these is bigger. So we're going to have to look at each of those decimal places. Well, it's the same up to the second decimal place, right? So if we evaluate it to the nearest tenth, they're exactly the same. But if we look over one more digit, 2 2/3 is bigger than the square root of 7. So therefore, we're going to say the square root of 7 is less than 2 2/3. All right, for 1.5 repeating and the square root of 2.25, we get these decimal values. Okay, this one ends, it's just 1.5, and 1.5 repeating is 1.555. Well, what does that mean? 1.5 by itself means the next digit would be a 0, right? So if we look to the hundredths place, 1.5 repeating is a bigger number. So therefore, 1.5 repeating is greater than the square root of 2.25. All right, pause the video, go ahead and check your progress on these three, and we'll go through those when you get back. Alrighty, here we go. Let's take a look at the square root of 11 and 3 1/3. The square root of 11 is equal to about 3.316. And 3 1/3 is 3.3 repeating. So which way would our arrow go? Which number's bigger? Well, the 3 1/3 is bigger because this digit, the next one over, is a 3, and that's bigger than the 1. Square root of 17, what is that equal to? Square root of 17 is 4.123, and this one is 4.03. So if we look at that hundredths, actually this one we can look at the tenths, right? 4.0 versus 4.1. That one is definitely bigger. The square root of 17 is bigger. How about the square root of 6.25? What is that equal to? That's equal to exactly 2.5. 2 1/2 is exactly 2.5, so this one we end up getting an equal to. Here are our solutions. Greater than, excuse me, that was less than, I said that wrong. Less than, greater than, and equal to. One of each on that page. Here's your chance to check your understanding. Go ahead and work on these 9 problems and bring them to class with you next time. See you then.